We're going to continue now with our next two examples of related rates problems. So this question involves a ladder that's leaning up against a wall that begins sliding away from the wall. And we're told how fast the bottom of the ladder is slipping away from the wall. And we're asked to find the rate at which the top of the ladder is sliding down the wall when the bottom is 5 feet away from the wall. So I can see here in the picture I've drawn, I've got a ladder that's 13 feet long leaning up against the wall, and as the bottom slides away, the top slides down. So we need to think about what is changing here. What are the quantities that are changing? And I hope that what you can see after a little bit of thought is that the two things that are changing are the distance that the bottom of the ladder is away from the wall and the distance that the top of the ladder is from the floor. And so I'm going to call x the distance from the bottom of the ladder to the wall. So this is x, and y is going to be the distance from the top of the ladder to the floor. Now we want to begin asking ourselves some questions. First of all, what are we looking for? What do we want? So let's go to the question, at what rate is the top of the ladder sliding down the wall? Well, if y is the distance from the top of the ladder to the floor, then what we want is we want the rate of change in y, which I write as dy over dt, when the bottom is 5 feet away from the wall. Well, that's the value of x. And so we want dy over dt when x is equal to 5 feet. So just for a quick second here, let's think about what units are we going to be looking for on our answer. If we want dy over dt, the units on dy over dt are going to be the units of y per unit of t. Y is in feet, t appears to be in minutes, and so we're looking for an answer that is given in terms of feet per minute. So we know that that's what we're looking for in this problem. What are we told? We're told that the ladder is sliding away from the wall at a rate of 0.4 feet per minute. We want to recognize that that's a rate of change in x, the distance between the bottom of the ladder and the wall. And so we're told that dx over dt is 0.4 feet per minute. Now we're looking at a relationship. Hopefully we can visualize that the wall and the floor form a right angle, and so we can see a right triangle here. And one of the relationships that sometimes we work with when we have right triangles is the Pythagorean theorem. And in this case, the hypotenuse is 13 feet long, and so our relationship is x squared plus y squared equals 169. Next, we're going to differentiate implicitly. X and y are both functions of time, so they're both compositions, and so we're going to use the chain rule. So I get 2 times the inside times the derivative of the inside, 2x times dx over dt, plus 2y times dy over dt, and that's going to be equal to 0 because the derivative of 169 is 0. And now we want to try to substitute in. Well, let's see. This is what I want. I want dy over dt, so I'm not going to substitute in anything for that. I'm told that dx over dt is 0.4, and so I'm going to be substituting that in right there, 0.4 feet per minute. And I'm told that x is 5 feet, and so 5 feet is going to go in there for x. And so the question is, what am I going to stick in for y? Well, this is another instance of the situation where we can use the relationship that we have a second time. And if we know that x squared plus y squared equals 169, I can plug in 5 for x and then figure out what y is. So we find y by using our relationship. Five squared is 25, so I subtract 25 from 169, I get 144. I get y equals 12 feet. So 5 is in feet, 169 is in feet squared, so I get feet squared for both these numbers. And so y is 12 feet. And so that's what's going to go in here. And so I substitute. And I get 2 times 5 feet times 0.4 feet per minute plus 2 times 12 feet times dy over dt is equal to 0. I'm going to do some algebra. So 5 times 0.4, if we multiply that out, is 2. So I get 2 times 2, so it's going to be 4 feet squared per minute plus 24 feet times dy over dt is equal to 0. So I get 24 feet dy over dt equals negative 4 feet squared per minute. Then I divide by 24 feet. Our foot in the bottom in the denominator cancels, and I get negative 1/6 foot per minute. And so when the ladder is 5 feet from the wall, the top of the ladder is sliding down at a rate of negative 1/6 feet per minute. Let's look at another example, number 4. This time we're told we have a conical tank, and the tank is 5 feet high and has a radius 5 meters high and a radius of 3 meters. We're told that water is pouring into the tank at a rate of 1.5 cubic meters per minute, and we're trying to figure out at what rate is the water rising when the depth is 2 meters. So here's on the left I've got my conical tank, and to the right of that I've got just a picture, a part of the drawing. I'm looking at the tank in profile and I'm only looking at half of it. So it's as if I took and divided this in half and then looked at it head on, and I would see that the tank is partially full of water. This distance is the radius of the tank, This distance is 5 meters, that's the height. And we're trying to figure out, so we first of all need to figure out what are the quantities that are changing. And so my quantities, I've got the volume of water in the tank, I've got the depth of the water in the tank, and I've got the radius of the water in the tank. And so R is right there, and H is right there. So that's our first step. What do we want? We want the rate at which the water is rising when the depth is 2 meters. And so we want dH over dt when h is equal to 2. What are we told? We're told that the water is entering the tank at a rate of 1.5 cubic meters per minute. That's the rate of change in the volume of the tank. So we have to think about a relationship here, and that's the volume of a cone. So the water, even though the tank is in the shape of a cone, the water is also in the shape of a cone. And the formula for that is, again, this requires probably doing some research in your text, but V equals 1/3 pi r squared h. Now, before we actually do any implicit differentiation, I want to try to actually come up with another relationship between R and H, so I don't have to differentiate using the product rule here. And so if I come back and look at this right here, I do have right triangles again, but I'm not going to use the Pythagorean theorem. What I'm going to use is I'm going to use the fact that the triangle formed by the water and the triangle formed by the tank are similar triangles. So this is another blast from our past that we want to use. And the thing that we want to remember about similar triangles is that ratios of corresponding sides are equal. And so in this case, if I look at the depths, I get h over 5, and that's going to be equal to r over 3. And so h over 5 is going to be equal to r over 3. Now, because I'm interested in dH over dt, I'm going to substitute in for r in this equation. And so if I solve for r, I get r is 3/5 h. And so I get 1/3 times pi times 3/5 h squared times h. And if I do a little bit of simplification, I believe I get 3/25 pi h cubed. Implicit differentiation time now, dv over dt is going to be equal to 9/25 pi h squared times dh over dt. And now I can substitute in. I'm told that dv over dt is 1.5 meters cubed per minute. I'm told that h is 2 meters. And if I solve, I'm going to let you fill the gaps in here, but what we wind up getting is that dH over dt is 75 70-seconds pi meters per minute, which actually reduces to 25/24 pi meters per minute. And we could write a sentence about this to express this relationship.